The learning objective for this lesson is to evaluate, analyze, and graph exponential functions. So what is an exponential function? Well, it's a function of this form. f of x equals a multiplied by b to the power of x, where a and b are real number constants, and there's conditions on a and b such that a cannot equal 0, b is positive, but b cannot equal 1, and x is a variable and it can be any real number. So we have b being the base and x, which is a variable, as an exponent. So please be sure to make a note of this. Now let's look at some real-world applications of the exponential function. So exponential functions can be used to model populations. Here is a picture of some artifacts found in Suruq al-Khadid, which is an archaeological site in Dubai. Now, archaeologists use the exponential radioactive decay of carbon-14 to estimate the age of organic material such as bone, cloth, wood, and plant fibers. It has many more applications in the real world. In example 1, we're asked to sketch and analyze the graph of f of x equals 3 to the power of x, and then we have to describe its domain, range, intercepts, asymptotes, end behavior, and whether the function is increasing or decreasing. Now, before I begin to sketch, for example 1, I produce a table of values. So these are the x values I've selected. I substitute these values into this function here to give me these y values. You'll notice the first three values are significantly small, and 81 and 729 are quite large. So on our grid here, I can only plot these 2 points. So we have 0, 1 and 2, 9. With practice, you'll start to recall quickly what exponential graphs look like. This one looks like so. Now that we've sketched this graph, we can analyze this graph to describe the following. Now the domain is just the x values. So if we analyze this graph, we can see that x is all of the real numbers. There are no points of discontinuity. So the domain is the open interval from negative infinity to positive infinity. The range is just the y values. So if we analyze this graph again, we can see that the y values increase towards positive infinity. And as the x values get smaller, the y values continue to get smaller and smaller without reaching 0. So for the range, we have this open interval. Now for the intercepts, you can see there's only a y-intercept here, which corresponds to this coordinate on our table of values. So we can say that y-intercept is at 0, 1. For the asymptotes, we can see the graph never goes below the x-axis. So in fact, the x-axis is a horizontal asymptote. Now for the end behavior, we look at the ends of the graph. So we'll begin by looking at this end over here. So as x goes towards negative infinity, what's happening to f of x? You can see f of x is getting smaller and smaller and approaching 0, but never quite touching it. So what we can say is the limit of f of x as x goes towards negative infinity is equal to 0. Then looking at this end, we can see as x goes towards positive infinity, what's happening to f of x, where you can see f of x is approaching positive infinity. So we can now say that the limit of f of x as x approaches infinity is equal to positive infinity. And finally, when we want to analyze the graph to see whether the function is increasing or decreasing, we always start from the left-hand side and see what's happening to the graph. So you can see, starting from the left-hand side, f of x is increasing and it continues to increase throughout. So we can say that this function is increasing on the interval where x goes from negative infinity to positive infinity. Now it's your turn to answer this similar question. So I suggest you pause the video before I reveal the answers. So the answers are the following. So for the properties of the exponential function, we're going to look at two types of exponential functions. The first one is exponential growth. So this is the graph for that. We have a y-intercept at 0, 1, and f of x is equal to b to the power of x, where the base b is strictly greater than 1. Now in our first example, we had this function, 3 to the power of x. So the base 3 is clearly greater than 1, so this is an exponential growth function. So what we did here was analyze the graph, and we discovered these properties in green. So in this section, we'll be looking at the extrema and the continuity of an exponential growth function. For the extrema, we look for minimum and maximum values on this graph. So if we try to look for a minimum value, we can see f of x gets smaller and smaller, but never quite reaches 0, so there is no minimum value. And if we try to look for a maximum value, we can see f of x gets larger and larger, approaching infinity. We can see there's no maximum value. So in fact, there is no extrema. For the continuity of a graph, we look at the graph to see if there's any points of discontinuity. And if we look at this, we can see there are no points of discontinuity. So we can say that this graph is continuous on the open interval where x goes from negative infinity to positive infinity. So we have the exponential growth function summarized over here. Now we move on to the exponential decay function, which is the other type. So the graph looks like this. We have a y-intercept at 0, 1. F of x is equal to b to the power of x, but this time the base b has to be between 0 and 1. Now the good thing is that the properties of the exponential decay function are nearly identical to what we have here, okay, except that they differ in their end behavior. And we can see that here, as x approaches negative infinity, the limit of f of x is going to be infinity, and as x approaches positive infinity, the limit of f of x is going to be equal to 0.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom, where we cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. The first session is always free. So if you are interested in a free lesson, click the link in the description below. To book a lesson, you can always send us a direct message on Instagram at Mr. Mathematics. Okay, with that said, let's get back to our lesson.
So in example 2a, we're asked to use the graph of f of x equals 2 to the power of x to describe the transformation that results in each function. Then sketch the graph of the function g of x is equal to 2 to the power of x plus 1. Now, first thing to notice is that the bases are the same. The only thing that differ are the exponents. So here we have x, and here we have x plus 1. So this tells us we can rewrite g of x as being equal to f of x plus 1, because all we did was simply replace the x with an x plus 1. Now this form will help us decide on the transformation that takes place. So we can say that the graph of g of x is the same as f of x equals 2 to the power of x, but it's translated 1 unit to the left. So here we have the graph of 2 to the power of x with an intercept at 0, 1, and we'll now put in some points that are translated 1 unit to the left, 1 to the left, 1 to the left, and I can sketch my graph of g of x in red as shown. So in example 2b, we have a question which is very much similar to the last one in 2a. The function f of x is still equal to 2 to the power of x. However, this new function h of x is equal to 2 to the power of minus x. So we can see here that the bases are the same, but the exponents differ. Okay, so we can rewrite h of x as being equal to f of minus x. We've just replaced the x with the minus x. So now we can get on to the transformation. So the graph of h of x is essentially the same as f of x is equal to 2 to the power of x. However, it's reflected in the y-axis. So we have the graph of y equals, or f of x equals 2 to the power of x. And I'm going to just pick some points that I've reflected in the y-axis to help me sketch h of x. So when we reflect it, the graph looks like so. So in example 2c, we just have a new function, which is j of x is equal to minus 3 multiplied by 2 to the power of x. Now 2 to the power of x is simply f of x. And all we're doing is multiplying it by minus 3 to give us this new function. So we can rewrite j of x as the following. J of x is equal to minus 3 multiplied by f of x, and this form will help us determine the transformations taking place. So the graph of j of x is essentially the same as f of x equal to 2 to the power of x, except that it's reflected in the x-axis because we have a negative number here, and it's expanded vertically by a factor of 3. So the graph of f looks like this. Okay, and all we need to firstly do is reflect it, which will give us this graph in pink. And then I'm going to pick a point here, and we can see this is -1. I multiply it by a factor of 3. So -1 multiplied by 3 gives me -3. And then this point will help me sketch the graph for g of x, like so. Now it's your turn to answer this similar question. So it says you pause the video before I reveal the answers. So the answers are the following. Now we look at natural base exponential functions. So what are natural base exponential functions? Well, they're functions of this form, where f of x is equal to e to the power of x. So you still have a variable x in the exponent, but whenever you see a base e, this is the natural base. So what is e? E is just an irrational number. Okay, and it's approximately equal to this number here. And it's named after the Swiss mathematician Leonhard Euler, and this is a picture of him there, which is often why we call it Euler's number. Now this base is the most commonly used base in real-world applications. So you should notice that e is greater than 1. So the graph of e to the power of x is very similar to an exponential growth function. So it would look like this, going through the y-intercept 0, 1. Now in example 3a, we have a question which is nearly identical to the questions we had in example 2, except we're dealing with natural base exponential functions, and we'll be using the same skills to answer this question. So we should notice that the bases are identical to these two functions, f and a. However, the exponents differ. So here we have an x, and here we have the x multiplied by the 4. So what we can do is rewrite a of x like so. So a of x is equal to f of 4x. So we've substituted the x with the 4x, and this form will help us when we're trying to describe the transformation. So a of x, the graph is essentially the same as e to the power of x. However, it's compressed horizontally by a factor 4. So it's within the brackets, so it'll affect the x-axis, and because there's a 4 there, it compresses horizontally by a factor of 4. So here is the graph of e to the power of x, which you should know already. And then we need to compress the graph to give us something like this. So you can see that the graph has compressed horizontally to give us this graph in red. So in example 3b, we have a new function, b of x is equal to e to the power of minus x plus 3. Now we look for similarities first, and we can see that they both have natural bases. Here we have the exponent x, and over here we have the exponent minus x. And then we have this extra part here, which is plus 3. So we can write b of x as the following. b of x is equal to f of minus x plus 3. So because of this minus x, I've replaced the x here with minus x. And because of this additional plus 3, I've put the plus 3 on the outside over here. And this form will help us with the transformations. So the graph of b of x is f of x, but it's reflected in the y-axis because there's a negative number here. We're multiplying x by a negative number. Okay, and here it's -1. And because of this plus 3 on the outside, we can see it's translated 3 units up. So here is the original graph, f of x equals e to the power of x. We reflect it to give us this. And then what we need to do is translate it 3 units up. So I'm going to pick this point here and translate it 3 units up. So 1, 2, 3. And I'm going to use this point to complete my final sketch. So here you can see the translation taking place. And then this red graph is my final graph. In example 3c, we have the new function c of x, which is equal to a half multiplied by e to the power of x. So if you look for similarities, they both have the same natural base, and they both have the exponent x, except in this one, the e to the power of x is being multiplied by a half. So I can rewrite c of x as the following. c of x is equal to a half multiplied by f of x. So you can see here, e of x, which is equal to f, we've just replaced this with f of x. And in this form, we can then describe the transformation. So c of x is the function f, where it's compressed vertically by a factor of a half. So this graph for the function f we'll use, and what we should notice is that this half here essentially halves every y value. So I've picked a few points here, and all we're going to do is this distance here we've halved to give us this point, and this distance here we've halved to give us this point, and then finally this distance here I've halved to give me this point. And I'm going to use these 3 points in pink to graph our final graph for c of x, which looks like this. Now it's your turn to answer this similar question. So I suggest you pause the video before I reveal the answers. So the answers are the following.